Is now? Is it working?
Yes.
Wonderful. Should we go? Should we start? Should we wait? Wait. Okay. No. Camera's on. Well, you can see it. All right. Good morning, everybody. Hope you're ready for the weekend. But before that, we have our fifth day sessions left. So thank you so much for joining. Really appreciate the time that you have spent with this. Yeah, would you mind? Okay. No, it's not Control L yet. It's full screen. It's not full screen. Thank you. Haji, is it wrong? Is it? Oh, yes, that definitely helps. Thank you. I promise you I knew that, but okay. Okay, so let's go ahead and get started. The topic now is drive cycle. I told you yesterday that when we were working on this, there's a couple of things I wanted to do. One was actually give you a little bit of the understanding of what the framework was supposed to be. We talked about the idea of NVH. We looked at vibration. We were looking at MEC-based methods, specifically about how you would model the circuits and such. So today I'm going to close the loop on drive cycle-based methods. So today, like I said before as well, what we're going to do is we're in a sequential fashion, but I kind of kept it in three separate segments, just because this one actually closes the loop on the R&D side that I wanted to focus on. Following that, there was one part that I wanted to talk to you about with the HEV suite using PSIM. For those of you who are familiar with it not familiar with it or want to try it, I have an example that we have actually included specifically because that gives you some flexibility that we have used in our classes and also in some of our research projects. At the end, what I wanted to talk about, what I wanted to include, if you saw the layout of the topics, it was looking ahead. I was initially specifically individual topics, but instead of making them all separate, I kind of combined them into a looking ahead document because we are setting. Instead of cutting out a full section, I tried to kind of combine them to where we still get all the content. Anything that might have been a little too much in-depth information, I kind of push that back a little bit. But anything you want to know from me, I'm more than happy to share. Okay, so let's get this going. Drive cycle-based analysis, right? So drive cycle-based analysis, as usual, we always start with the numbers we wanted to go with. We know what we're trying to do. We have a 2025 targets. We want to hit power electronics, cost, volume, motors, cost and volume, and then you have the traction drive, cost and volume. So we know what our goal is. And where this will actually start to make sense again is towards the very end. I actually will give you a breakdown of what the cost, in order to get here, what is it that we are hoping to accomplish? Like we cannot really, I mean, nobody can tell you a system is going to cost you this much cost without telling you how much each individual component is going to cost. Because how do you know how much you can spend on motors? How do you know how much you can spend on sensors, auxiliary units? So there has to be a method to the madness. So how do you get to this point is really what we are going to try to break down in the third part of this course today. So like I said, the idea was each of our drive, even though our expectation was the same, and we now have drive cycles. But the problem is each of these vehicles have a different drive line target. What this basically means is that you might be looking at 15 miles per gallon for one situation, but they don't start and stop at the same time. They don't have the same weight distribution. So what that means is that our goal for 2025 compared to 2015 basically means we have lowered almost all of our metrics by quite a bit. I also have a comparison of 2025 and 2020 that you will see later, and see specifically that we are still aggressively pursuing numbers that make us have to control or innovate to create the right outcome. So in terms of power density, what you see here is that we have an 843% increase, which means you're going to go 8.5 times what the numbers were barely 10 years back. Actually, 7 years back even now. Power level, we want to double it in 10 years. We want to have about 100% increase in reliability. So now we want our drivetrain to last us 300,000 miles, not just 150,000 miles. And the power electronics is going to be 50% cheaper. So as you can see, we want everything to be higher except for the cost, which we want to cut down in half. Without a doubt, you cannot create a solution that fits all of these metrics without looking at the overall system. So we looked at different ideas of what we could do. We touched on individual components. We looked at thermal management, NVH. We looked at windings and steels. We also looked at an idea of integrated drive design. Actually, we looked at it a little bit. We talked about controllers and power electronics. What we're going to do today is we're actually going to combine these last pieces. So that will, this is just a vision that I have in terms of how I would want to achieve something like this, which I'm more than happy to get some feedback from you. So the idea of the integrated drive framework really is to develop a flexible and time-efficient framework that you can do within the optimization framework that also considers the drive cycle. You want to include the multi-physics domain, and you also want to do current shaping. Like I said before, what you need to do is you cannot do it sequentially, because sequentially it is difficult to manage one without adding a ton of time to your simulation time. So the approach really is you start with the drive cycle, you create the surrogate model, and you do this couple optimization. We talked about this yesterday. Today we are going to bookend this topic with the first and the last task in this project. So if you look at the current drivetrain target, like you see between 2020 and 2025, the numbers have changed even there. We're trying to reduce just between 2 years back and 2.5 years from now. We want the numbers to be 30% lower, which means we want the cost to go down, and we want a power density. Actually, I miswrote this. It's 89% increase, not decrease, reduction. So it's not a reduction. So we're basically trying to make sure it goes up. And I had my reference here, which somehow I eliminated. There's a couple of things clearly I missed in terms of my references here. So, but the idea really is when it comes to the 2012 drive system, $30 per kilowatt, to now 2022, we had $8 per kilowatt. And now we are trying to go to $3.30 per kilowatt. So the numbers that are changing are quite aggressive, which means in order to consider this outcome, we need to have highly efficient motor designs. We need to have materials, which is not something we are focusing on right now. We need to have manufacturing methods, thermal management, additive manufacturing, and high performance computing. We are trying to focus right now on the first and the fourth topic for the purposes of this project. So if you talk about the design optimization of the electric motor, it has multiple steps involved in it. The first one is actually the multi-domain, non-linear, strongly coupled problem description. You want it to be an application-specific design rather than being too generic. You want it to go beyond the electromagnetic design. You don't want to stop just by calculating the magnetic fields and leaving it at that. And you want it to be an iterative process. There is value. While I keep saying that we should look at analytical methods, there still needs to be a way to close the loop. So we need to make sure there is a mechanism that evaluates the fitness of the solution that you have designed. How well does it actually meet the criteria that you are trying to design for? So in terms of computer-aided tools, you have the development of concepts and engineering analyses. You have naturally coupled domains, and you have a way to visualize the outcome that you have gotten. Bottom line is, how can you make sure you got what you set out to do? Of course, that ties with complex simulations, time-consuming, and resource-intensive processes. So you're trying to do all of this, but you have a trade-off that actually comes with computer-aided tools. So which means there's always a trade-off. You're always playing a tug of war between how accurate we want it to be and how much it is going to cost us. So in terms of the challenges and approaches, you can take a look and you can see that it tends to be quite a bit. The current methods that basically we have here, classic methods, tend to be computationally expensive. They're time consuming, especially if you're trying to simulate for a large number of operating points. Now, this should be a good time for me to also mention what representative points are. So I will talk about that later as well. But when you design any system, right, we talked about, especially for the electric vehicle, our tractive force that we calculated on day 1 or 2 or something, that tractive force is translated into a basic relationship between torque and speed, right? So that torque and speed tells you what the motor specifications are going to be. And I'll show you in just a little bit based on our calculation. If you use torque and speed data derived from the drive cycle, the number you are designing it for, which by the way, when you're designing a typical motor, which operating point do you normally design the motor for? If you have a torque speed curve, constant torque, constant power, typically, where is your motor most likely going to be designed for? Which point? Which spec? It's the base speed, right? Base speed is what? Base speed is the point at which you go from constant torque to constant power. So you typically design because that's your maximum torque point with the maximum speed. Well, that's the base speed, and that allows you to go into your constant power region. So yes, so we design exactly for base speed. That gives you an idea of where you would like this motor to be. The question is, does that motor that you're trying to design, does it fit the application that you're trying to design it for? And that's what basically is a representative point. A representative point basically is a point. It's like a weighted sum of how many times, if you do a statistical analysis and across the drive cycle, you create a cluster of points that tells you what torque and speed is required for the entire drive cycle. And then you do statistical analysis to identify what number most adequately represents one given cluster. And you allow it to create specific operating points that you can design it for. Keep that number as low as possible because you want that to be optimal, but not so low that your motor, like I showed you yesterday, we had some of the motors in which you change the speed of, or change the DC link voltage of the Prius, and you see that efficiency map moves left and right quite a bit. So if you design the motor for base speed, but you're operating at, let's say, 20% above base speed almost all the time, now what? Now your efficiency is not at the 94, 95% you wanted it to be. Instead, it's sitting somewhere to the tune of, I don't know, 90%. I'm just putting numbers up. Which means now you might end up with a method that tends to be non-systematic. You are designing a system like a black box. You are not looking at it as a solution, big outcome that will definitely meet your application's needs. And that basically means we start talking about the idea of data clustering. So if you talk about data clustering, computer science, if you look at big data, most of these applications today, they look at those kind of options, right? If you're talking about reinforcement learning, artificial intelligence, I mean, like there's a whole slew of big data science or of data science that is currently in use. Mainly that has been enabled because now we have the computational resources. It's not because that these methods were not known or understood before. We just didn't have the processing capability that made it worth the hassle in a lot of cases. We also couldn't get a large pool of data. So your AI and ML concepts are only worth the amount of data you have available. You had to train your system with data that is available. And that we will talk about a little later. So data clustering, basically, we use a method called X-means. There are different methods for data clustering. There's K-means, X-means. We also look at this, the trade-off between the optimization objectives that we had and the cost function that we have described, which in our case was actual computational cost. So we also established that 3D FEA is very time consuming and analytical models tend to be less accurate and are not as flexible, which means you don't have the option to change the geometry just because you want to. If you change the geometry, you might end up going back to the drawing board. And the other day when we had one of the questions about whether if you have an existing data point and you wanted to modify the design because you have already collected a lot of data, having a system that actually evolves, something like a geometric evolution that evolves the design rather than makes a 1-point calculation is always going to save you time in the long run. And of course, we've talked about the surrogate model. We already introduced that before. And then you have the conventional excitation that you typically have. You don't normally look at current. Whenever you're designing a machine, you're always assuming I'm giving it pure sine. You have not considered what the constraints of your power electronics are. What if you cannot switch fast enough? What if your sampling time is too sluggish and you actually are expecting it to sample and give you a signal back at, I don't know, 300 or 500 kilohertz, and a system cannot go above 50? And that happens. That's happened to us as well, in which we found out that if we can go to 200 kilohertz, everything works. They said, like, well, 200 kilohertz is the upper limit. We said, all right, 200 kilohertz. And they said, oh yeah, we can go up 200 kilohertz, but we don't want you to. We would like you to stay well below. So what I'm trying to say is that the application might have a specific requirement or specific constraint that sets how far you can go. If you have multiple cores, you might have the option of doing a little extra post-processing. If you don't have multiple cores, you might be limited in how many pins you have, in how much data you can store. You might be limited in the stack size that you have available, which means you have to figure out how you're going to collect data, process the data, and then send it out, all before the conditions of your motor. Simulation is beautiful because it can be time in, right? You can do a 5-hour simulation in like 5 minutes. Why not? But because your system is repeating itself very, very quickly. But when it comes to something like this, when you're trying to implement that on hardware, or you're trying to do this with a bunch of designs, you have to take every single hour, every single minute that you're spending on this into consideration. So in this case, so we are looking also at combining design process with the current estimation process. So we are trying to establish what profile of current is needed specifically to get the performance that you're looking for. So you define so basically what you're doing is it's something like a Newton-Raphson method, like I said before. It's just like what you do for power systems. You don't necessarily have to know the answer. You just know what your boundaries are for each one of them. You keep iterating until all of them are within the error tolerance that you have. And once you meet all of them, you're good. It doesn't have to be the exact number. And depending on how many iterations you go for, you get that much closer, right? You're basically converging to a solution. The idea here is quite similar. You're trying to converge to a solution, except that instead of doing a ton of simulations, I'm converting that into a bunch of surrogate model-based drivetrains. So this is now where we are going to start. We start with the drive cycle. The drive cycle actually gives you a torque speed profile. The torque speed profile gives you what's called RPs, or representative points. So let's start with what it looks like. So the optimization can basically have a single or multiple operating points. Why? Well, because that's how your system could be. It really depends on, you might end up with a system in which your clusters, your point clusters are close. There's only 2 of them, because it mostly operates into these 2 of these modes. It could be something like an HVAC system where you don't change your operating speed very much. It has some movement. But in a drive cycle where your speed versus time it varies so much, you end up with the torque speed spectrum that moves a lot around. So this is the WLTP drive cycle that now translated to this torque speed map. What this tells you is that if you are designing it for, let's say, the torque speed profile that you would normally have, like, oh, sorry. Okay, so if you had designed it for something like this, if this was your torque speed profile, and this is what you had originally done it for, you typically have designed your motor somewhere around here, right? Instead, now what's happening is you're looking at, so if you design for this motor, now look at this here. Your points, this point here, the high speed operation doesn't happen that much. The low speed operation, now you're designing it for this point here. So let's say you have your highest efficiency point like this, somewhere here. You're operating a lot in this region. So now you see you are now fairly distant from your highest efficiency point. So if this was, let's say, about 94%, this might be somewhere around 90 or 89%. So you see what happened here. So it's not that the original design was wrong. It's just that it was not designed to be optimal for your given system. So what we are talking about basically is converting this into a map where you look at these clusters. Okay, so you create these clusters here. There's one cluster here. There's one cluster here. There is a small cluster here. There's a big cluster here, small one here, and a small one here. So keep in mind, the cluster is not necessarily sitting on the points. It is coming from the points where it operates. You're trying to get a point that is most representative of what your operating points need to be. You're trying to cut down the number of points. Otherwise, you would have had 1 point here, and you would have had 1 point here, and 1 here. So you see that number would go up quite a bit. So the trade-off we are talking about right now of trying to extrapolate, how few points can I run with? Can I get away with an efficiency that is going to be high enough? It doesn't have to be the best option. So for example, if you're looking at something like a sync rail, you're talking about a sequence reluctance machine, and your goal is to design and place the flux barriers in specific points. If you have a model that allows you to look at the application, it allows you to look at what the operating points are, you can design specifically what your output. And by the way, this method is for torque speed, but what we realize is that this also applies to machine design as well. You can actually look at the sensitivity of which variable gives you the best performance and cluster them together, and then only optimize for the points that make sense. Because think about it, when we talk about the idea of switch reluctance machines and such, even there's certain variables, if you change, they make a big difference, but some you change, it doesn't do a whole lot. Even in DC motors, you change the field current, it will not change your torque as much as your armature will, because your back EMF is going to start ticking up again. So the point I'm trying to make is that any system you design can use information where you're trying to look at a cluster of operating points, but for this purpose, we're just looking at the drive cycle, not the overall duty. So okay, so here's the idea. So the point here basically was, we want to cluster the data points, find out how they're related to one another. You define the clusters, define the representative points, and then you set optimization weights. Why optimization weights? Because once again, just because you have a point here doesn't mean it's the highest utilized point, right? So you need to set a point for whether or not this has value. So each one of these operating point has a weight to it. So you tell it, I want it to be designed mainly for this point, and then this, you set a hierarchy of which point has more relevance. And as you go forward, then you start to break it down into giving you the maximum efficiency. So the hope is that you will get, keep doing that, wrong point, sorry. So when you go here, the goal is, let's say you want this to be your, let's say, hierarchy of 1. You want this to be, this cluster to be 2, and then you want this to be 3. You want this to be 4, this to be 5, and this to be 6. I'm just putting numbers out there. This is not necessarily what we use, but I'm just telling you in terms of hierarchy, you can define which operating point will get the most weight in terms of how you're going to operate. So the arbitrary range split, you can have a couple of ways, a few ways to do your cluster definition. You can either have an arbitrary range split, which basically means you look at it. It's like what I just did right now. I just look at it saying like, it looks like the red ones are the best. I'll design for that, and then maroon ones, and then blue one. I'm just making it up as I go, right? And that's doable, that's possible, but now it's not reproducible. It's not repeatable. I do it now, I give it to somebody else, you're going to get a different result. So that's another challenge. You want this result to be repeatable so that the optimal point is actually that the idea of a local maxima and global maxima, you're trying to actually optimize it for anybody using it. So it should be user agnostic. Of course, then you look at the energy distribution, and then method, and then you have k-means, and then you have x-means. So these are basically statistical methods, the bottom two, that you are actually trying to use data clustering methods to identify. Statistics, basically. The RPs basically is you either create a geometrical center of gravity, which once again, you have the points, you identify where you're going to land, right? You can either have an energy center of gravity, or you can have a method or algorithm based. So we went with the method or algorithm based, in which we would identify what the points were. Based on that, we defined the optimization weights, energy ratio or density of operating points. You can pick whichever one you want. Once again, when I say whichever one you want, you are defining it based on what your application needs. So that's what gives us here. So if you look at an arbitrary range split, it basically splits the range into segments. So you have rectangular clusters with different torque and speed levels. It's relatively straightforward because you basically have segments. In each segment, you identify where should my point be. Easy enough. and you place it there, you optimize it for that. So now it's an arbitrary, but the problem is it's very non-systematic. Like I said, you have to have the user, okay, you have to have the user that defines your range. Do I need to have multiple points, few points? I am coming up with a number that is best suited for me, or that I have capacity for. I don't want to do a whole lot of calculation, I cut it down. The number of clusters can be arbitrary. Am I looking at the cluster, like here, the range I created based on where I saw the clusters. If I drew that line somewhere in the middle of that cluster, now I have a problem, right? So if I drew that line, instead of being in this range, if I drew that line here, and let's say I drew this line here, and this one is here, it's fine, and this one was, let's say, here. If this was my cluster, right? What would happen is now I have a point that here for this region, I don't really have much of a point, so I end up somewhere here. This one is so densely populated, now I have it here. So all of a sudden, even though you have a cluster that you have created, the cluster does not represent where it's supposed to be, because the user was not necessarily aware of what they were trying to accomplish. So once again, the idea of automation has a lot of value, and also doesn't adapt to the. Okay. So it does not adapt to the distribution of points, which means your system is such that if your data points changes, it doesn't change with it. It still says, like, I'll do a point of between 0 to 4,000 is 1, 4 to 8,000 is 1, 8 to 12,000 is 1. I set the points before I knew anything, which means I'm not building a resolution that's based on the amount of data available. I'm arbitrarily assigning the clusters. So there are basically a few papers who've done this. So this one actually was done by one group from 2016. There's another group from 2014, and Lee did this in 2017. So if you look at these points here, this is actually closer to what we wanted to do. It means they have whole working points and they have an operating envelope, much like what we're talking about as well. So if you look at the energy distribution, you have a number of representative clusters are extracted, and you basically have the variation is set out on your torque speed plane. The idea is fairly straightforward. You are still using statistics. It's not changing much. It's simple to implement. You consider the operating point's energy as opposed to looking at the actual value. You adapt to the distribution of points. Once again, non-systematic. Once again, user defined, and once again, arbitrary number of clusters. So I guess at this point, the point I'm trying to drive home is the fact that you need to start having something that is repeatable and can actually be verified by somebody. You cannot have somebody who comes in and say, no, I know this better. It's not like driving a car. It should not be so arbitrary that somebody can always do it better than you. There should be a method to the madness. Okay, so the next one basically is called k-means. So k-means actually is an interesting idea. This is where we initially started. We started with the idea of creating k clusters. The idea was basically you create a predetermined number of clusters. So in this case, you have k clusters where each point belongs to the cluster that is nearest to its centroid. So the idea itself was reasonable. That was where we wanted to go. So there were several people that had actually done something like this, where they look at each range that creates that cluster of points, and they assign a value to it based on the magnitude. They calculate the centroid and say that centroid is basically my point that I'm using. It is a systematic approach. It does adapt to the number of points you have, but you are still defining k, which means somebody is telling you how many clusters to go with. Now the question is, how do you define that? We're not saying it's wrong. None of these methods are wrong. All of these methods work. The question really is, what is the optimal method that you can establish that creates something that is repeatable and reproducible? And the number of clusters, like I said, as a consequence of k, now your number of clusters remains arbitrary. Right? So I'm hoping at this point I'm making sense more than trying to convince you of the fact that this is the way to go. That's not exactly what I'm saying at all. I'm just saying, look at your system. You have your overall objective. Look at the system before you start designing. If you start designing and then hope you hit the number you want to go, that there's a very good chance you don't. So x-means is the method that we actually used. X-means is essentially refines the cluster assignment specifically. It keeps breaking it down into subdivisions, and it keeps the best resulting splits until you get a Bayesian information criterion. That's a big factor that you get. That big is basically the point that tells you how many clusters your system should have. So it keeps splitting your clusters over and over again, trying to figure out if you get the right number of clusters, will this still represent the points you need? The benefit is that it's systematic, which means you get a significant accuracy and computational cost. It adapts the number of points. It gives you optimal number of clusters, and it basically allows you to have, compared to visual inspection or any of these methods, it gives you a much more thought out approach that is users free, and the optimum number of clusters is automatically determined. So you don't have to select how many you need. We actually did a comparison, specifically show what happens if you have more than that number of points. It's something like a harmonics, right? I mean, when you do the harmonic analysis or Fourier analysis, you go up to a certain number of terms, right? The order of harmonics you pick, 3, 5, 7, 9, whatever it is, and then at some point you say, like, if I add more, it's not going to change anything. Sure, it'll give me like the 4th decimal point of accuracy, but I can live without it. Same idea. So you're doing something in which you're basically saying, I could do with 7 points, but do I need 7 points? What if I could get by with 4? How do I make sure I'm doing that? Because keep in mind, it's not only electromagnetic. I'm taking it from electromagnetic, I'm coupling it with vibrational, taking it acoustic noise, and doing thermal, which means every single one of my points is going to cost me a lot of time and a lot of resources. So I cannot afford to do that many times. This is actually one of the examples we have. By the way, we have papers that you can take a look at later as well if you want. So this one actually is, the idea was we took an IPM and we wanted to create a method for identifying, basically doing analysis to see how would my operating point change, how would my performance change if I used each one of these methods. So we did the optimization on a single operating point. We did it on x-means, which gave me 2 points, and then we went to k-means that gave me 7 points. So our method says 2 points good. K-means says, well, based on the clusters, based on what I'm seeing here, if you go back to clusters, that's this one here. This one. You see this 1, 2, 3, 4, 5, 6, 7. There's 7 points here. So K-means by visual inspection, or basically when you broke them down in terms of the centroid, you said 7 points, that's a good representation. But we said, based on our calculation, we found that 2 could get the job done. Once again, it's a starting point. You might not get the right answer, but we had to see what the variation was going to be. The application was for an IPM for traction, electromagnetic model only, because we had to start somewhere. And then we did 12 design variables for geometric optimization, and your drive cycle was still the same, WLTP. What that means is that we are trying to look at 12 components of your design spec. So you're changing the rotor length, the back iron, the thickness, the arc length. So you defined 12 variables that we wanted to optimize for. Keep in mind, now those variables are being optimized for electromagnetic. You will then also be looking at vibrational. You'll be looking at thermal. So that many design variations, looking at every one of them is definitely going to be time intensive. So here are the time points here. It's the distance between the magnet and the rotor OD. You have the notch that was created. You have the length of your slot, the pole, width of your pole, the back iron. So you had a bunch of variables. We defined 12 of them. So based on that, we essentially calculated what our drive cycle is going to look like. And if you break it down, this is your cluster, right? So when you look at this breakdown, this looks easier to spot that where the points could possibly be. But what happens is if you look at something like this, the colors, in my mind, the colors kind of bias you just a little bit. Because when you look at the colors, you start looking at those colors clustered together. Right? You look at the same points without any filtering, then you kind of think that maybe there's only a few points that you need to work through. So you have this point here, you have this point here, you have this point here. So maybe you just would have gone with this. You would never even have thought of going all the way out here. Not because you didn't, but because the point here was, when you have a different color, you look at the orange, say, yeah, all the oranges cluster here. I'm not saying, once again, this is not supposed to be a bad thing. It is, keep in mind, this was supposed to help somebody who's doing visual inspection. It allows you to actually separate the components out for yourself. So instead, you can see this one basically with blue comes out at 2 operating points that we defined. So we said this point here and that point here should be able to represent our values accurately. So this is the overall torque speed profile that you get versus efficiency for all 3 of these methods. If you do the optimization if you do the design for a single point, you see your optimal point is somewhere between around 4,000 RPM. When you go to x-means, you're still around 4,000 RPM, but that range actually has gotten wider, it's gotten bigger. If you go to k-means, once again, 7 points, it's still big. But guess what? When you look at the numbers in terms of efficiency, x-means and k-means gave you nearly the same amount of efficiency. So the question is, if you got this in efficiency, I'm not saying x-means has to be better. I'm just saying it has to be faster. Because I'm not just looking at how efficient my design is. I know most designs work. Heavens, if you use FEA and there is no visual inspection, you just keep designing the motors and kind of drive it crazy, you will get a good design eventually, right? It's just a matter of how long all that takes. So what we found out here basically is, in terms of the normalized computational cost, your k-means actually took 1. Your A, which basically was single point, took 0.11, and B, which is our x-means, took 0.25. So that's the computational cost. So clearly x-means is more expensive than a single point. But then we knew that. I mean, the first one had 1 point to be evaluated for, the second one has 2. So that's not any there's no surprise there. Average efficiency here 96.4, 96.2, 1 point is 95.2. So this will start changing. Now once you start modifying the design and all the variables, this is the peak efficiency. You will actually start to see these numbers mean more in the simulation. What that means is that if you increase the number of representative points, does not mean your system is going, the design is going to be better, or your system is going to be any more accurate. That was the primary lesson. Is there any questions around from this one so far? Okay. So based on that, basically this is the efficiency improvements when you have more RPs, where you can get your cycle efficiency goes up, but your normalizing computational cost goes up along with it. So you're not necessarily benefiting in terms of the improvement that you're going to get from one to the other. So going one step further, these are the relative efficiency maps that you're getting. And if you look at the clustering that you get based on the optimization, you can actually design your motor for the operating point and evaluate the behavior. So just the intermediate conclusions here basically was that you can have a method that gets automated. So if you have a design criteria that have been defined for you, you can put that into your model, allow it to calculate how many RPs you need, and come up with a time efficient calculation method that fits into your drive cycle algorithm. Take it one step further. So now we talked about the front end, next to the back end. The back end basically is the optimization. Like I want certain current, I want certain design, I want certain control. I want to combine this. This idea basically was something called simultaneous coupled optimization. It basically means we have coupled both of these behaviors. We have the electromagnetic and we have the control behavior. We combine them together. You have a current profile variable that is given to your system, the controller, and then you have geometrical and typical profiles given to your design. You start to optimize them simultaneously, and the coupled approach basically means your geometry and current profiles are considered at the design stage, while the constraints are provided to your current profile optimization. So you have a nested system here where you basically create a current optimization for each design. So you run a design, run an optimization, and then take the next design, run an optimization. So it's a simple nested idea. We do this in Simulink all the time, right? You basically create a nested loop, one loop on the outside, one loop on the inside. But it's never possible to do this kind of a design procedure because FEA takes a long, long time. You cannot run an optimization for every single point of FEA if you do this. And that basically gives you this combined framework where you can give geometrical variables, geometric design variables, and then current variables, and get a final design directly from it. Yeah. Can you repeat that question? Oh, this one was actually all. So this one was behavior model essentially. So what we're doing is so if you remember the surrogate model I showed you yesterday, that surrogate model goes and nests inside this. So it is a Simulink model that we had. The entire thing was done using mathematical models. So co-design. So it depends on how you're defining co-design. If you're talking about the entire design being done at the very inception, this was the method being developed. So we did not design the motor in this scenario. This is just the framework for the design itself. If that makes sense. So the proposed approach basically to your question here is that you have the optimization for the geometry. It's done primarily with sinusoidal currents, right? We always assume that the currents are going to be sinusoidal, which means we don't look at the harmonics. We don't look at the third harmonic, which is the dominant frequency. Your ideal waveforms with no harmonics basically would be sufficient to get a smooth ripple-free torque. Great, except that it doesn't work because your system will not be smooth and ripple-free. is there going to be harmonics in it, and you have to take that into consideration. So all your methods that you have basically have an you have to have an injected harmonics that's specific that you're going to use. So the idea basically here is that you perform a current optimization on the geometry, and if you do that, you will not necessarily get a combination. It's like a matrix of geometry versus control to see which map fits the option best. And that's what the goal is. So simultaneously, you introduce both the geometry and current, and you essentially give the designer one extra degree of freedom in the optimization process. That means they can decide what the geometry is going to be while they are deciding what the current is. So typically, when you're doing a controller design, you don't have that degree of freedom. Geometry is not a luxury you have when you're designing your controller. So this gives the designer one extra degree of freedom, where you can use current to control the geometry, or you can use geometry to control the current, as the case might be. So, okay, so this is the IPM description that we had. We had geometric optimization, coupled optimization with the two methods. We had the electromagnetic model only, and this is the equation. We evaluated 4,800 designs. So the number of designs we evaluated were pretty high. So we came up with the Pareto front that goes with it. This is geometric optimization. We defined the Pareto front that goes with it, and we did a coupled optimization like what you were saying as well. What we did was we compared geometric optimization with the coupled optimization to see what the performance results are going to be. When you compare the candidates for coupled optimization, you get a torque that is closer to the first geo method, but the torque ripple is much lower. In this case, we were trying to optimize it for ripple. Why? We had to pick one criterion. This was establishing or validating whether or not the method works. This was not necessarily designing the motor itself. So we got a much lower torque ripple. We got the torque ripple for the other geo was much lower, but the torque was low as well. So if you look at the percentage losses, 1.7 loss kilowatts of losses, 1.6, 1.44. So this might have slightly higher losses, but you are able to get a much better torque ripple and the highest torque possible. Our objective function was torque and torque ripple. So this gave us a number that specifically told us what the design should look like and how the geometry should be. So based on that, you basically use design 2, and you came up with, well, we came up with a specific coupled approach that you could identify. And we took that one step further to do this for an SRM. So what you saw yesterday also was a surrogate model we created for a switch reluctance machine. We applied 10 variables. We wanted to look at total torque, average torque, and the total losses in the motor, and we evaluated 4,800 designs. We had a test setup here as well, and what you see here basically is the maximum torque actually follows the experimental profile very nicely for FEA. We used the same profile, and we identified what the SEO and vibration model from yesterday, what that optimization looks like. So based on that, what we identified essentially in terms of observations was that the drive cycle integration into our design process allows us an extra degree of freedom. By having X means you're able to use data mining, you're able to use statistical methods to identify to establish a trade-off between how much time things take and how much accuracy you're going to get. And based on the surrogate model, we actually got a much better vibration behavior, and the method itself shows that it's possible. You have to develop them individually, but once the model is set up, the computational burden on your designer is going to be substantially lower. Any questions in terms of what you have? So I just want to kind of add this slide here, I guess, just to go over this, the value proposition for anybody who wants to look at this. You have a shorter lead time. You have a bunch of late design modifications, like what you said. What if you have something, or I think one of you guys said that you have existing data and you want to change something now. Can I change it? Yes, you can. So it actually allows you an option to change the variables without going back to the drawing board entirely. You might be able to make small disturbances in your design process. So it's going to be very good for drop-in replacements. So if you have an existing motor that you want to design the controller for, and you want to say like, I want to keep the same stator because the winding and the stator I want to keep the same. But what I can do is I'm okay with changing the geometry of the rotor. So tell me what I should do. What would be the best method? How much skew do I need to get? Where should I place my flux barriers? Where should I put my slots for the synchro? I had an induction machine. I want to convert that to a synchro. How do I go about that? So you can change the geometry based on this and allow your system to tell you where you would place. Now, the process, the more you start to get picky obviously the process gets a little more involved there as well. And of course, it's a systematic approach, which basically means that you are not going to over design the product. You're going to get something that's going to be optimally designed. There's a few references actually included here as well. This is available on IEEE Explore. You're more than welcome to take a look at it. If you have any questions, we have a few more that we're following up, like I said, on kernel-free method and such, where we are taking this one step further and looking actually at the electromagnetic behavior of the machine and modeling it mathematically. So actually, wait, that's a repeat slide. So on that, I'm going to go to the next one. But before we do that, I wanted to see if you had any questions. Yes, no? Okay, yeah. Higher. Mm-hmm. Yes. Correct. Right. Correct. Correct. So real time basically means in the simulation, right? So if you're getting, so this, a simple answer to that would be yes, in the sense that we did not do the modeling here specifically. For us, it was not one of the constraints that I had put on my system. Now, if you are doing that, you can convert your flux distribution or field distribution, which is what we're doing here. You can convert that into using Steinmetz equation. You can calculate core losses, and then you can calculate copper loss based on the current. And based on that, you can calculate how much losses you're going to get for the motor. So yes, it's basically like a Venn diagram, right? I mean, like if you have 3 Venn diagrams, you have 3 subsystems and 3 operating ranges. The more you introduce, the narrower your overlapping points will get. So yes, you can, but the chances of you not having any of the designs fit your criteria could go up. So you could have a constraint which indicates that, or you create a plot like an inductance plot of a switch inductance machine. It creates a plot which shows you could pick this. But once again, that moves away from being an automated process into being a user heavy. Like, how do you get to decide where the motor is going to go? So yes, it's possible, but you have to just think through what your computational burden is going to be, but more importantly, how okay are you with a design not meeting all of your criteria? Because that is a possibility, right? So, but that's a good question. Yes, I think the visual would be nice. We did not take it that further, that much, or we did not take it as far with this specific project. We were just looking at the outcome for torque, but that's a good idea. Okay, if there are no other questions, we have actually a couple of options. Either we take, I went a little over, so either we take an early break and come back for the next group. This is actually like the PSIM model based idea. So I'm not going to take a ton of time with this, but what I'm going to do is basically we're going to cover what the PSIM simulation looks like, and then I wanted to go into the looking ahead piece. So what we can do is we have 5 minutes, we're 5 minutes early. Let's go ahead and take a 5-minute early break, come back and catch up here. So it is right now, it's 10:55 by my watch. So maybe we can come back at 11:05 and restart here. We'll go for an hour and then close out. All right, excellent. Thank you. Okay. Ooh, wow, it's a little later than I thought. Okay. Welcome back, everybody. Let's go ahead and get started here. So I'm gonna, like I said, the next few minutes that I wanted to spend was on this, on the system level modeling. It's more of an idea of trying to show you what the system level modeling of the vehicle could look like using PSIM, what we have done, and what we were able to get through. So a lot of it really is information that you might have already seen somewhere, or you might have used it yourself. But I will try to go through this reasonably quickly, and then we'll spend more time at the back end talking about what this means for all of us. Okay, so PSIM basically is a software called, and this was actually one of the topics that we had, if you remember at the very end, we were talking about HEV simulation using PSIM and using magnet. I included ANSYS in the beginning to show you how that works. I couldn't find a good way to integrate this, so I kind of let it stay separately. So basically, it's very important right now that, I mean, no matter what you do, on one hand, I'm saying that yes, it is important to be analytical. On the flip side, I'm also saying simulations are absolutely necessary. So this is not me contradicting myself, it's just trying to let you know that my view or my idea on all of these things is that any advancement is good, and any improvement that you make is going to be good. Of course, it depends on how you use it, but besides that, if you're able to use FEA in the best possible way, you will get results that were better than if you didn't. So the idea was basically, the CAD we were using here was for power electronics electric machines, but then we modified that to get HEVs. Previously, we used to build our own domain, and once they released the HEV suite for PSIM, we started using it. So oftentimes, the idea is that simulation software really rely on mathematical models. They are behavioral models. If you want to look at vehicle simulation models, you have software like Autonomy. Autonomy is developed by Argonne National Labs. There used to be an old one called Advisor, which was developed by National Renewable Energy Labs. Autonomy is not free. It is actually available at cost from Siemens. They manage it. And then, what's it called? Advisor used to be free, but then they discontinued the software, but it was free vehicle simulation for quite some time. Of course, Simulink has its own version now that they have created, and PSIM is the one we've been using for quite some time for our courses. So I just wanted to quickly mention that. The reason I like this specific software is because it's, first and foremost, it's got a, it doesn't have a very steep learning curve, but more importantly, they had specific tools that were useful for our courses. So if you take a step back here, your motor design and PSIM, you need to make sure that you know what you're designing. If it's a high efficiency drive system, you might be looking specifically at options like electric cars. And generally speaking, if your drive efficiency is going up, in that case, you might have two specific components that you're trying to meet. First one is you want to have, for the same range, you want to have lower system size, lower charging time, and lighter cars. For the same system, longer range, fewer stops, charging, and performance. So sometimes these can actually be models when you're talking about simulation or co-simulation, in which you embed the model into your software to allow it to run in a system mode. It can be done. So they actually have a tool that combines with GIMP. They also have something that combines with Infolitica, which I should mention. I have no connection to the company, so I'm not talking about them because I know them or I have some stake in it. I'm absolutely unbiased. I'm an end user. Is all I do with it. Just want to make sure it's very clear. I have no interest on whether or not you choose to use it. So the HEV design suite, really, this was the one that I actually liked. The idea initially I had was that towards the end, I was hoping we would do something like a demo in which we could run the simulation, but knowing that video and doing it in real time would be challenging, we created this handout that allows you to go for. So it really is a dedicated tool to design and control your power electronic drivetrains for different EVs. And the goal, of course, is that you can have different models. You can have an HEV, PHEV, HEV nonlinear, with PHEV with nonlinear. And the goal basically is whether or not you are looking at the drivetrain that has a linear or a nonlinear model of a PMSM. So if you use your magnetic field changing or not. So based on the drivetrain that you need, essentially you can select what kind of motor you want. You have the engine generator connected, the DC bus, and this really is the plug-in hybrid electric vehicle. So you have a grid-tied system, you have a battery that connects to it, and the benefit basically of this suite is that all the parameters are closed-loop controllers. So basically, you can put the number in, you can run the simulation, you can get the results, and whatever you get, you can go ahead and verify whether or not it works. So this part really was, we use this, we actually use some of these models. We also use them in some of our labs as well, in which we allow students, we have built a drivetrain, we built an electric vehicle and an HEV emulated drivetrain specifically, because we wanted to let the students to apply their own torque profile. So it has a gear, it has a brake and a throttle. And students can actually apply a drive cycle based on what they see on the manual. And based on that, they can look at the state of charge, the depth of discharge. They can look at the energy, the current profile, and that kind of stuff. So that's part of the hybrid vehicles course that we have. This is basically allows you to look at the drivetrain design, and you can look specifically at the variables of battery voltage, battery current, speed, torque, and such. They have a model specifically that this is actually just for Nissan Leaf, but you can do the EV powertrain. And just to kind of give you an idea of what this looks like, this is an example where we had for an HEV tool for the design suite. You have a battery model, the traction motor, the DC bus, vehicle load, system parameters, and of course you have the simulation clock on top. And the goal really was trying to make sure you are doing a pre-design check to see what you are going to design and for what, and how it's going to look. The HEV, if you want to look specifically at, they actually have a couple of vehicle models, I think, that they use, but this allows you to look specifically at the traction drive where you have a battery. The only challenge is your battery model is not going to be as accurate as you want it to be, which means they will have a generic model unless you know the internal specs for the battery. That can be a little different from what you're going to get in real life. The same thing with traction motor as well. It will give you a basically it'll give you the ideal or the or rather their version of non-ideal motor parameters. If you want to modify that, you need to have specs specifically that you can import into it. You can change some variables, but keep in mind one thing it doesn't do. It does not do electromagnetic. So you're talking about a motor that already exists. You put in the number in, and you're going to simulate that. The steps really is, I'm going to, like I said, I'm going to show you what this looks like, and then we'll move on to the future looks. So you can do the simulation clock. Once you go in there, you can actually develop the simulation model. And if you basically, if you choose free run, the simulation will not stop. It will just continue to run the entire time. So the system parameters block really is a text file. It is essentially is just like your MATLAB M file. If you double click on the icon, you can actually change the parameters, which is what you have, you see here. So that's the flexibility they did not have before, which we actually liked. It allows you to change a lot of the parameters. You can go in and change specifically the shaft time constant, the motor variables and such. The battery we used was lithium-ion battery. You can change some variables, like I said. You can change it to be a certain number in series, certain number in parallel. But that means if you have something like an 18650 versus a 21700, you only have so many variables that you can play with. So you have to select what numbers you're looking at, and you can place the voltage probe specifically to look at what your state of charge is going to be. In terms of traction motor model itself, you can connect that directly to the DC bus. And if you double click on the icon, you will get this inside the traction motor. So you can actually modify the overall schematic of a traction drive, which basically includes a motor and the inverter, and it also has a motor controller. So what you have is, that's a typo there. It has the motor is a PMSM model, not PSMS. And the inverter is a conventional 6-switch 3-phase machine. So in terms of the motor controller model, you can apply a speed and torque profile that sends a reference to the controller, and that basically takes it to the torque controller. So if you're doing something like what we just did, in which you want to apply a specific profile for torque and speed based on the design you came up with in your drive cycle based analysis, you can put the number in. It will run a bunch of simulations, and it will give you the circuit level simulations, not just model level. For the EV, it will allow you to do speed control, and in the torque profile control as well. And the speed profile that we typically select for our case is piecewise linear. I've had some questions as in the past previously about what model we have used. I'm more than happy to point you to the models we have used. If you have any questions, you can let me know offline. You can also put the variable name, and the benefit basically is that if you do that, you can directly identify what your output is going to be without having to guess what waveform you're looking at. The vehicle load basically is from PSIM design suite, in which you can use 2 voltage probes and torque. We measured that. And when you take it further, you can apply the drive cycle for the vehicle. Now, what it does is it looks at your vehicle drive cycle. It does not look at the drive cycle as it applies to your motor. So it has its own limitations of where you are going to be able to modify it. Now, if you wanted to do the drive cycle itself, you can create your own drive cycle specifically. You can actually define different parameters for it. You can have base speed at a certain value. That's a torque speed profile. You can select what your value, how wide is going to be. So it does everything like an electromagnetic system without being an electromagnetic system. So it simplifies the system quite a bit. And the reason I'm even talking about this is because a lot of times when you're doing the drive analysis, you either have to do co-simulation, like I said, or you have to do something like this. And as I mentioned to you previously, we have walked away from some FEA tools specifically to give us the option to do them using something like FEM. Still FEA, but we're trying to simplify to make it open source, or basically do a free software. This is not free, but the reason we're using this is because it gives us the flexibility of looking at each individual device. Whenever you create a model on Simulink or something like that, oftentimes it would be a small signal analysis, right? You basically create a model of the switch, which is represented by its on-state resistance. You don't really have a switch, which means you might miss out on things like its turn-on spike. You might not have the overshoot from the turn-on. You might not have the inrush currents and certain variables that circuit-level simulations would have. So to simulate it, we basically have to follow a set of sequence. You select the mode, speed mode control, put the actual order per unit values, set your maximum parameters, and then of course, go into the drive cycle, set a simulation time, and run it. For the EV drivetrain as well, the same idea. You can actually set, this is just one example we used. We set a base voltage of 48 volts, 80 amps, and ran the entire simulation, and you can set it to operate at a specific drive cycle. So if you do the simulation here, in that case, the EV gives you two specific drive conditions where it shows you what the torque is going to be in Newton meters. And this is, sorry, torque is going to be, time is going to be in seconds versus torque in, versus speed in RPM. So you basically have a profile that looks like a drive cycle that you can simulate. We put this in, we just kind of gave it a relatively linear profile. You can change that if you want to. And that basically, once you run the simulation, you get the SimView window that tells you what output is available and where. And that you can use specifically to get your results. This was velocity versus time that we had, and that actually tells you how fast this vehicle is going. We gave it a very general, very generic information, but it does show you the motor profile. The place where this actually is helpful is when you start integrating not just this vehicle model, but when you start dropping in FEA into it. Once you start doing that, then you are able to look at behaviors like faults, which normally, like I said, would also have an element of harmonics into it. So if you're looking at faults and failures in the machine, you can actually modify the geometry from a parametric sense. In terms of drive cycle 1, we got the results here. It basically shows that the state of charge is depleting over time. This next time, we basically did the same drive cycle. We were now looking at the traction motor for phase A, B, and C. You can see that the load profile was changed at one point. We went from 15 Newton meters of torque to 5 Newton meters of torque, and the vehicle speed basically changed accordingly. The same thing we did for drive cycle 2, in which we went for the battery volt that takes a dip, and that basically takes you to the next level of simulation, a hybrid vehicle. I hope you don't mind the fact that I'm going through this a little faster, not necessarily because it's not like I don't want to spend time on this, but I just feel that this is good. I wanted to cover this, but I don't want to miss out on what we have done before or what we're supposed to do with the demo. But this just gives us a little more flexibility if I'm able to go forward. But if you have any questions, I'm here. So this part actually uses series hybrid electric vehicle, and this will be available. So if you want to go home and you're running the simulation, you can download the software or get the software from the company and use them as you see fit. This is a series hybrid vehicle. We actually do this for the engine model, and part of the reason is when you're talking about electric motors and you're trying to replace the engine with an electric motor, you need to figure out what your profile is going to be. So in having a baseline model like this that allows you to simulate each variable one at a time, allows you to provide what kind of motor, how much, what the motor size needs to be. You can also set up a parameter in which you limit the traction motor available and see what the performance, the acceleration and such is going to be for the motor. You can use the engine model specifically. You can also import models that have been provided, and they're developing more of them as we go forward. So if you look at the generator inside, you'll actually see a detailed model that goes into the blocks, and you can modify the circuit as you see fit when you're doing the simulations. You can set up the generator parameter controller model, see what outputs you want to see, and your input to the generator basically is connected from the mechanical side, and the output is connected to the DC bus and goes towards charging the battery. So if you look at it, the series hybrid vehicle, everything else the same like an EV, not much different. And you can set the parameters specifically to run the simulations. Drive cycle is similar. It's basically a constant power that we are looking at. So the battery profile, basically, this is the charging. It's running in generating mode. The engine's operational. Your battery is charging. The vehicle is moving forward. You draw current. And then at some point, the generator goes into coast mode, and your vehicle starts to basically, it's not charging or discharging as you go. You can also make the vehicle operate in battery drive mode only. We turn off the engine, just apply a switch to it, turn off the engine, and it allows your eigenspeed of the engine speeds to actually be equal to 0. And that allows you to essentially go into a coast mode in which you are talking about using only the motor. So in a scenario in which you're trying to identify whether or not your battery pack is large enough to get the range you want, you have an AEV 100 or an AEV 300, which is basically all electric vehicle range. You can decide whether or not it's going to be able to. This is the state of charge, battery current, and the battery voltage profiles. And once again, depending on the profile, when you change the operating point, your results change correspondingly. And you can also look at what happened to the motor. Was there a fault or failure that happened along with it? The last thing basically is you can look at the generator torque, speed, the battery voltage, vehicle speed, torque, and the traction motor variables. This is all done in normalized quantities as with which is a time versus speed drive cycle, where the engine was set to operate at a constant speed of 2000 RPM. This basically is this is one example where I would really have liked to have you all have a simulation model where we could have done this one at a time so you could play with it as we are seeing. That would be a very good demonstration that I would have liked to do. Maybe at some point we can do this off and do it over Zoom if we get a chance to. You can also do this for the engine and the battery itself, in which you have the battery voltage, current, and SOC that you can identify, and that tells you what the vehicle speed and vehicle torque is going to be. From that, you can calculate for the change in your torque that you get. You can actually calculate what your currents for each phase is going to look like. So that's where I'm going to stop here. I know I went super fast through this, but yeah.
This whole model is the
It's a number, so you can put in a number, but they don't design the transmission for you, but it's a number you can put in. They have a Toyota Prius model that is a lot more detailed, but it's difficult to look inside. You cannot look under the mask as easily. Correct. That's where the challenge we found. So having something a little more generic without the transmission was okay.
What they have presented basically for a differential which is normal mechanical differential.
Yes. Correct. Yes, it's a mechanical differential. Except for the EV, you actually have the EV I think was single torque. So yeah, it would also be a mechanical differential. I don't think it's an electronic differential. Four-wheel drive, you would have to modify. So they do not have a model. I've only seen models for a rear-wheel drive or a front-wheel drive, which basically would be the same model mostly, but they do not have anything for a four-wheel drive that I have seen. They are open normally to for you to ask them. The tech folks are more than happy to provide support, but they don't have. So it doesn't do everything. It gives you a good connection point with the circuit level simulation, and that's why I wanted to kind of just have this in there for a demo. Yeah.
As you cannot export or import any model from Infoletica to the PCIP. So you need an analytical model for that.
There's a plugin. So they actually do have a plugin as well. You can actually, they had a plugin. They should still have it. They definitely have it for JMAG, but I think they have it for, they used to have it for Infoletica as well, was a plugin. I know Simulink in particular definitely has a plugin that goes with Infoletica, but I think PCIM, I believe, also has one. They're coming up with a new one for Flux. Flux 2D, which is the same company now. They got bought out by Altair, who also owns Flux. So, but JMAG is the one that they have historically connected, like what Joe's saying as well. So yeah, so this is a good tool. It's an effective tool to get to where you want to go. But like I said, it's a very good tool to do lab exercises with and to do a demonstration. The reason I wanted to, like I said, have this is so if you go back and play with it, you have a reference, hopefully, that specifically looks at each individual drivetrain. We looked at a few more options there. Okay, so let me do this. Let me switch gears here. And looking kind of as we close out, because we have the next round that we have at 3 p.m., we're going to have the Q&A session. But what I wanted to have was just spend a little bit of time talking about the looking ahead part. Because, yeah.
The session will be just after lunch. That will be experimental component,
Yes.
hysteresis band current.
Yeah.
So probably it will start at 150.
Yeah.
Then your session, Q&A session will be 215 onwards.
Okay. Sorry,
Either
I
2
stand
or
corrected.
215
So okay, so I stand corrected. Two to three, I guess, would be something like that. Yeah. Perfect. So this is the one actually, like I said, I combined a few of these topics that I really wanted to talk about. And the course, really, the reason why I wanted to look at this, I had to think about how I would want to frame this. Please keep in mind, this is not supposed to be prescriptive, meaning it's not supposed to tell you what's going to happen next. Because let's face it, we don't know. The Department of Energy has a lot of information on what they think will move the needle for something like this. I have included a lot of information from there. And then a lot of my perspectives based on what I have read, I added those in as well. But please make sure you understand that this is meant to be a starting point. By no means is it meant to be an answer to any question. If you start off, when you start talking about electric vehicles, the basic idea is that we have established vehicle models. This is the Prius. We've talked about this a few times now. And this was developed for a 201 volts DC bus. It has a smoothing cap. You have a motor inverter that connects to the motor. You have another generator that powers the generator, right? So they are connected in parallel to your supply. You have a DC-DC converter. It's a bi-directional converter. It charges and discharges the battery. So you're able to step the voltage up from a 200 volts bus to 650. So you can basically go for a range of 201 to 650 volts. Now, if you look at the actual schematic itself, what you will see is that this is a 2010 Prius model. You will see that the boost converter is placed in the front end, followed by the generator power electronics, and then you have the motor power electronics right next to it. So we've established that this trend is something that is a compact design. The Prius has done a really good job. So we're not trying to question what anybody's doing. What we are trying to ask is, what do we do next? Like right now, the question that came up is, where can I apply this technology? Where are the ideas? What are the improvements that we should be hopefully trying to accomplish as we go forward? So I want to start off right out the gate talking specifically about the challenges. Let's start with that. So the first thing is, if we're talking about design of electric circuits or power electronic circuits, the first challenge that you always have is selecting components. You have to decide what you're going to have, what kind of circuit you're going to get, what kind of device, wide bandgap versus silicon, selection of switching frequency, because that translates into losses, right, and cost. And then, of course, you have the selection of passive components. That takes you to magnetic elements that includes inductors and transformers, and also includes selection of a capacitor. Selection of a capacitor might not seem like a big deal. There's a company called SBE Electronics, if I'm not wrong, who actually their entire business is building capacitors, electrostatic capacitors, and they're polymer film capacitors, essentially, if I remember correctly. But the point I'm trying to make is that the idea of selecting capacitors is a very big task when it comes to power electronics, in particular traction motors. We'll talk about that. In EMC analysis, you can analyze the electromagnetic emissions, EMI. You can also look at the, that's S missing, determination of switching transients and the optimal circuit layout, minimize parasitics, right? You need to identify how your system is going to operate. Mechanical and thermal design, you're looking at loss modeling, thermal management, and packaging. The last one in particular is not something that we talk about very much. There are folks who are in devices that deal with it, but oftentimes as electrical engineers, we don't think about bonding, and we don't think about the wire bond that you're going to do or any of that stuff at all. Packaging, dies, basically, how is that going to happen? The wafer size. We don't think about that really, because we assume we are circuits and beyond. So we don't often think about that. However, in order to have the right kind of impact, we need to take that into consideration. So if you look at the drivetrain targets, it's actually EDTS, not here. Like I said before, the numbers have changed, where the number was $8 per kilowatt, then it went to 25% cost reduction to $6 per kilowatt, 2025. The power density goes from 4.0 to once again, I made a mistake. I made several mistakes today. It's 3.3 kilowatts per liter. So in terms of the power electronics itself, you are going from the cost of $3.3 per kilowatt down to 2.7. So 18% reduction, 87% reduction in your power density, increase in your power density. I've made that mistake a few times today, haven't I? My apologies for that. So power volume reduction, it is going to be one reduction is fine. This is power density, your volume. No, it's fine. This is fine. No, it is fine. This is okay. I'm second guessing myself with everything now. So it's basically is a volume reduction that's happening, not power increase, but a volume decrease instead. So in terms of your targets for your onboard charging, you have a few key variables. You have cost, weight, volume, traction drive and vehicle integration, functionality. You have fast charging and wireless power transfer. So there are several topics that we need to have innovations for. Now, in terms of the cost, how are we going to get there? You need to get to a cost where the DC converter targets would be less than $50 per kilowatt in 2020. Now you're going down to what? $30 per kilowatt. And I'll share a little bit of the path forward that they have defined as well in terms of how we could even do this. There are a few pointers as to what this could look like. Specific power, it goes up from about 1.2 kilowatts per kilogram to about 4 kilowatts per kilogram. So you're more than tripling the amount of specific power you're going to get. The power density goes up quite a bit. Efficiency is still going up. So the point is, we're trying to make it cheaper, but we want to make it more efficient, which basically means you want to make it smaller. For the onboard charger, on the other hand, you are going down in the cost. You go from 50 to 35. Specific power goes from 3 to 4. Power density goes 3.5 to 4.6. Efficiency, as usual, goes up. So if you look at the traction drive itself, for a cost of $6 per kilowatt for a 100 kilowatt system, or a peak 33 kilowatts per liter for a 100 kilowatt peak system. So you're looking at the targets that we had in 2015, 2025, 2025 versus on road, and 2025 versus 2015. So you can see what has happened here is that if you compare what the numbers we have today versus what we had 10 years back, but once again, this is the target. This is not what we are trying. This is not what we have right now. So 34% drop in the cost, 7 times, 7.5 or 7.25 times the power density. We are trying to get, once again, for the motor, we want to drop more than half the cost. And for the power density, we want to increase it by times 9. Yeah. So typically, so these are done by, usually they are going to be user groups who sit together to decide. So this is done by the Department of Energy, and they come up with user groups. And as I understand, which I have limited knowledge of what happens behind closed doors, but generally speaking, they have several national labs who come up with their estimates of what would make these technology or like EV commercially viable, what the tipping point is, and all of the numbers are calculated backwards, specifically to go. Then they look at where the current technology is and decide what that leap could be in the current season, based on what delta they see in the technology potential. After that, you also have, and they will admit to you that the numbers they're putting are always aggressive. So whatever you think you can do, they'll go 1.5 times that. But not quite exactly that number, but they will actually overshoot what you think you can handle very easily. They will, because the objective here is that they want you to try something that normally you would not have tried. A 10% increase, 15% increase, most people can think of something that would make it work. Might not be as effective, but at least you have a starting point. They want people to think completely outside the box. So we have funding agencies called Department of ARPA-E, which is basically is the Advanced Research in Power and Energy, I think, and yeah, something agency, and then E stands for energy. I forget what the ARPA is for. And then Department of Energy. So there's 2 windows. ARPA-E is the more aggressive of the 2. Department of Energy is more industry driven, but it has slightly faster integration time. So if you are looking at some of the reports that they submit, that's usually what we go with. Most of the time, we are defining our design targets, power density and such, based on the numbers that the Department of Energy puts out, because that is what the companies are trying to meet. Oftentimes, policies tag team with what the Department of Energy says needs to happen. So they start putting a number saying you need to have a miles per gallon that's going to be like, I think they had said 50 miles per gallon is what they were expecting by 2035 or something like that. So they were looking at very specific numbers, which don't quote me on that either, but they tell you specifically what number would make sense for example, for carbon dioxide emissions to go down. So they look at the numbers and they reverse calculate, saying that we need to have this many cars or this many electric cars. In order to have that, the cost needs to be here for this many vehicles being sold. For this many vehicles to be sold, the motors have to be this expensive. and for them, the vehicle size has to be this small. So it's a long drawn process. It's not something they come up with overnight. So it's a fairly labor intensive process, and it's done primarily by DOE, but I believe it's done in collaboration with all the national labs and several stakeholders. So this actually is their math. If you look at it, they're talking specifically about the challenges in power electronics. The cost itself has two components. You have the power module and you have the passive components. In terms of volume and mass reduction, oftentimes they tend to be run by passive devices, your inductor size, your capacitor size, right? Those are the ones that are going to dictate how the unit is going to be. Keep in mind, going to high frequency with wide bandgap devices goes beyond just the ability to operate at high temperatures. You also have the ability to go at high frequency. When you do that, your passive devices get smaller. So there's the very real value in going to higher frequencies of operation. In terms of packaging and advanced material, you need higher temperature capability and you need better thermal conductivity. For reliability, you need to look at wire bond, like I said, die, substrate attachments, solders, connectors. You also need to look at substrates and epoxies. In terms of thermal management, liquid cooling to air, single-sided versus double-sided cooling, and for efficiency, whether you want to be in idle or quiescent load, what that would look like. This is the overall breakdown of what we think right now the cost of a power electronic system basically would look like. So you have the majority of the cost is currently being consumed by the power module. A very large component of that is consumed by the terminals, the block terminals, the bus bars, and then you have miscellaneous here, which covers everything else that is on the device side. You have controls that goes to 11%. So this is where currently the cost breakdown is. Now, yesterday we had a question specifically about whether or not your sleeve could be conducting. So I actually did go back and take a quick peek at it just to make sure that I was not completely off. So yes, so stainless steel definitely is one of the components. So if you talk about the first technology that I feel is of relevance, of importance here, the first one is going to be high-speed motors. So when it comes to high-speed motors, your EV traction requires you to have high starting torque. You need to have acceleration requirements, high power density for volume, high efficiency for battery range, and wide constant range for having a single gear transmission. So if you're able to operate the motor, you can eliminate one gear set. If you only have basically a single gear transmission system, now your efficiency cascade doesn't basically get your efficiency down too much. The challenges here are that because you're operating at higher speeds, you can end up with high voltages and fluxes. That's the challenge. The second thing is you have mechanical limitations. Keep in mind, when you're talking about bearing friction, you can have bearing losses that will directly affect. As you go faster, you can actually end up getting more losses. You can also have ventilation losses to nonlinear friction, and you can have vibration that are caused by hysteresis. The second thing is when you go to higher voltages, because you're going to higher speeds, that causes you to have high stress on your power devices. So you need to have devices that can handle higher voltage levels, unless you want to actually combine them in series and parallel to increase their voltage or current rating respectively. The loss for these sleeve materials can also affect your cooling and efficiency. So sleeve materials can be basically carbon fiber, stainless steel, titanium, copper, iron alloy. I put copper again. Sorry, it's copper, iron alloy, and copper. So you can have any of these, which some of them are conducting, which basically means you are going to have some losses that you are going to get from that. So thermal stress or higher loss per volume, which basically comes from your copper, core, and windage. And that directly influences the power and the lifespan of the system. It can affect the insulation of the system, and it can also cause your magnets to demagnetize. We know that temperature has real effects, some of them. So I tried to add references wherever I could for any of the data that I'm claiming or any of these facts that I'm claiming for this. So this one actually is from the paper by Reddy. It actually is a conference paper specific that shows the carbon fiber sleeve that is mounted around the magnets. And what you do have is primarily it's to centrifugal force can make your magnet fly. That's basically what the job of the sleeve is going to be. Now, if you go to high speeds, you have some additional variables that you need to take into consideration. First and foremost, you have to look at your bearing. You have to look at the shaft that you're getting. So if you're talking about the high speed, you need to figure out what the resonant frequency of your system is going to be. This is basically for a high-speed PM machine and the entire rotor for the motor. So basically at what frequency they are vibrating at, the first thing you're always trying to do is you're trying to move the mechanical system, basically, as like you were talking about as well, you're trying to move the mechanical system as far away from its resonant frequency, right? So your possible mitigation techniques basically could change the, you can increase the inner diameter, basically adding more stiffness. You can reduce bearing span. You can increase the shaft wall thickness, making it more rigid. And you can have a third center bearing, which will balance it out a lot better. And your modes will basically change. In terms of managing high-speed operation, you can have a solid rotor for integrity. You can have a rotor stress, basically can be managed by managing the tensile strength of the material. You can have multi-level inverters that will allow you to reduce the total harmonic distortion, the harmonic content in the drive, and use wide bandgap devices. It is very interesting to see that when we are talking about high-speed operation, everything starting from mechanical design all the way down to device selection has a role to play, right? You're talking about passive elements, you're talking about the mechanical structure, the shaft size, all the way to wide bandgap devices at the frequency they operate. The second technology that I felt was relevant for this conversation is additive manufacturing. Has anybody here heard of the phrase additive manufacturing before this? Yeah, so I guess we're not going to be a camera that can talk. So additive manufacturing can basically, if you kind of simplify it, it's essentially referred to oftentimes as 3D printing, right? It's basically 3D printing when it's not necessarily it's not a entirely accurate description of what additive manufacturing truly is, but it's a fairly well established or accepted replacement phrase. So the idea basically is you manufacture the part. The true definition will be you manufacture the part by layering materials using a digital model. You basically add layers to it. That allows you to design the unit. So you can have 7 types of AM that I was able to, when I was looking at the types of AM, this is, by the way, is not a very well developed technology, meaning it's still very new. There is a lot of work that people are trying to do. In terms of PhDs, I would imagine this is going to be it is, in my mind, going to be a game-changing technology. It's just lots of unknowns in this entire process. So for people who are looking at PhDs or advising students and such, I'm not saying you need to do this, but it forms a very open-ended problem challenge statement as it currently stands. So you can have a VAT photopolymerization. You can have material jetting, binder jetting, material extrusion, powder bed fusion, sheet lamination, energy deposition. None of these are topics that first and foremost I work on. So AM is not something that I'm currently working on. However, it is something that I do intend to go into at some point. The challenge, of course, also is that you need to have the fab capability to manufacture something like this. But there are teams that are doing it. A lot of teams are actually based out of Europe and some in China as well who are working on this. So in terms of emerging AM technologies, additive manufacturing technologies, you can have dot forming technology, which is basically for high performance, high precision productivity for metal manufacturing. And then you can have AM of pure copper and precious metals for designing your windings. Is actually, these are 2 3D printed units. This is a rotor, it's a switch reluctance machine rotor that was 3D printed, specifically done by a research center in Finland. And then you have the state and rotor assembly that was done by Oak Ridge National Lab in the US. If you look at what an AM system looks like, you can basically go into iron core. You can look at permanent magnets. You can make a thermal management system, the cooling system. You can have the mechanical parts and structures, and you can have the winding. So all of them are capable of being 3D printed or of being manufactured using AM. What challenge, if any, can you imagine? If you're doing additive manufacturing, what are some challenges that you can imagine? Sorry? Staircase effect. Can you explain that just a little bit more?
So since it is a layered manufacturing, there will be, for example, powder bed fusion. We call it as the direct metal laser sintering technique, where the powders will be and the hot laser will be
Mm-hmm.
So while following the CAD geometry, what happens, the entire surface of the product or the design becomes a staircase kind of thing. So finally, it needs to be
smoothed out.
Post-processing has to be done.
Exactly. So the idea basically, I mean, basically, when you do something like this, the point here is when you have something like powder deposition, essentially that you have, or powder bed fusion, it creates this ridges on the outside that basically it starts to kind of move a little bit away from the edge. So you essentially have to burr it down, or you have to grind it down specifically to get the smooth outside, or the smooth structure that you're expecting to get. So it's not an easy enough process where anybody can do it. You need to know what the manufacturing process is and what the challenges are. Yeah. So if you're doing something like, if you're using basically something like soft magnetic composites, you use something that you are going to add to the system, you are automatically creating, so it doesn't have that same structure. Like it's like compact. If you remember, we were talking about SMC back in the middle somewhere. We're talking about the fact that when it's compacted, you don't have to have laminations because there is no idea of a lamination. The entire thing is stacked and it's compressed. So you don't need to have laminations for eddy current, just by nature of what you have used to manufacture it. So no, in this case, you won't need laminations specifically to manufacture this. The way you are putting it together, it'll automatically, because you are layering it, so it actually automatically creates some axial separation. So it will stop the eddy currents, but once again, that's a very manufacturing specific process where my knowledge there is limited in terms of how much or how little of a lamination we can create there. But as far as I can, for the methods that I have seen, typically if you're talking about a method like using powder bed fusion is the one I have seen as well, that will actually give you a natural basically isolation in terms of electrical system. But along adding to that, you will actually structural integrity questions, right? Oftentimes when we associate anything that is 3D printed, the first thing that is always of concern is whether or not it's going to be as easy. So this one actually is, that's a question to be answered. I don't have an answer for that. It's still something in improvement. Based on any number of papers I saw, nobody has said that they have actually been able to, I don't think I saw any papers commercially developed AM method for a commercial application. So this actually is the variable profile copper for concentrated winding. This was done by the University of Bristol. As you can see, majority of them, or at least a good chunk of them here, are being done in Europe. So if you go one step further, so now we talked about the idea of power electronics, or now we talked about machines, additive manufacturing. Now we're looking at the inverter. So sorry, the first one was high, and then we had manufacturing, and now we have talking about the inverter. So this is essentially the layout that tells you what each vehicle is, like different vehicles that are available. They're all electric vehicles. It tells you what the DC link voltage of every one of the units is, what the max frequency is, what the power level, power density, and specific power is. The reason this is useful information to have is it tells you what the industry trends are. In particular, this actually goes, this paper specifically was from 2021. So they had information all the way down to 2025, which is what the DOE targets are. And the last number they had essentially was for the Model 3. The Tesla Model 3 essentially has a DC link voltage that is 375 or 400 volts. The max switching frequency is 900 hertz. It's a 200 kilowatt system, which has the power density was not published, so they did not post it. Specific power also is not known. So Tesla does not send out, I believe at this point they are manufacturing their own motors as well. They're not getting it from outside. They are in-house manufacturing, so they don't post all the data available for the units. So when you talk about inverter design, there are a few bottlenecks that you need to work through. The first one is wide bandgap devices. Wide bandgap devices at high frequency essentially would allow you to get the power density we are going for. You can also use a concept called segmented inverter. Has anybody here heard of a segmented inverter before? Essentially, you are separating the inverter and the machine into two different components. So you're running them separately. So you basically allow the DC ripple to be reduced by having two separate units. There's two switches that are connected in parallel, and then you have two windings that basically connected in parallel as well. So that allows you to separate the power level, lower the ripple. It also cuts down your EMI, switching losses, and basically can, of course, it can have a multi-physical problem that you have to solve in terms of electrical, thermal, and mechanical system, because now you have two windings, you have two sets of switches. EMI switching from this power converter is something we do need to take into consideration. As you go into higher power levels, higher power density, you will have to take into consideration what kind of harmonics is going to put out. That also includes cooling. So cooling we talked about at length. Cooling of power electronics really needs to be done using passive active devices. It can also be a combination of both passive and active devices to have a hybrid cooling system. What does it look like for a DC link capacitor? Because if you're talking about the inverter, you also have to go in further to the DC link cap. Like I said before, DC link caps oftentimes are broken down into two types of capacitors for the traction system. You can have an electrolytic capacitor, which is considered to be a very popular choice. We've all seen them. The other one, but they tend to have a short lifespan. They have a limited current conduction, and they have a operation. What that means is that they tend to be bigger. The second kind is electrostatic capacitors. These capacitors are non-polar construction. They basically are the film capacitor type. You have plastic film, ceramics, or anything like that that's used as a dielectric. The polymer film capacitor used as a DC link cap can be reliable. They have a high current conduction. They have high frequency capability, and they have lower losses. They are also a very expensive component to buy. You can have plastic or polymer film dielectric that actually gives you much lower temperature dependence. The challenge is the change in dielectric, it does not lead to much change in the dielectric characteristics, but the relative permittivity of these dielectrics is quite low. That means you end up with a larger design for the capacitor than you would do otherwise if you use something else for your dielectric. The last one that I was interested or intrigued by is the idea of a glass-based dielectric. And that essentially allows you to, it tries to overcome the challenge that you get in terms of the high breakdown voltage. So if you're trying to operate the system at much higher voltages, in that case, you can use glass. It's got much better dielectric properties. The challenge is, like anything else, is glass, right? Which makes it brittle. It can break, and therefore it is susceptible to damage. One step further. Now we talked about the motor, we talked about the power electronics, we talked about a little bit of the devices. Now we are talking about integrating all of them together into one single unit. So there are a few people who have done quite a bit of work, or several people who've done a little bit. But the idea of an IMD or an integrated motor drive is that you establish the power electronics inside the housing, right? So you can have it either around it, you can have it in front of it. Different people have done it different ways. This is specifically a project that was represented by Professor Jin Wang. He's from Ohio State University in the US. The goal basically of an IMD is that you are able to remove the drive unit enclosure. You can have one single cooling system, so you can share the coolant loop through it. You can also eliminate the drive to wire power cables. So the drive to machine. How is that useful? Well, the first thing, if you have ever done anything, I've talked to you, I think we talked about this at the very beginning as well. If you have ever done a PCB design, the first thing you want to always try to do is minimize the cable length. You're trying to make sure you don't create a loop, because that throws out a lot of EMI. But by fundamentally embedding it inside the motor, you cut down the length of the cable quite considerably. In terms of efficiency, I'm making a lot of mistakes. It should be boost. So system level efficiency can be as high as 30% for a drop-in replacement, which means by embedding your drive into your motor, you can lead to an overall increase of 30% in the efficiency. This was done for a pump or fan application. Keep in mind, pumps and fans are all units that are not used for traction, but they are used in your automotive system, right? I mean, you have a coolant pump, you have a pump for a fuel line, everything has a pump, whether brake line or anything, including your windshield wiper. They all have pumps. And then on top of that, you also have fans that go, whether you're talking about your AC that's going out or your radiator. So in terms of the fault tolerance, all the machine leads are internal. That is a huge benefit, because specifically, if you can actually increase the number of machine phases, and that means that your impact of phase loss is going to be substantially more practical. So essentially what I'm trying to say here is that if your drive itself is sitting inside the unit, in that case, the amount of windings, the amount of wires you're going to require is not going to be as high. So in many ways, by adding the drive by setting the drive within your motor, you cut down the length of the copper, you cut down the length of the extra windings, and the feasibility of increasing the number of phases goes up. I'm not saying there is not a cost involved. There is still a cost involved, because you're still winding that many motors, but all you're adding primarily on the outside is on the devices. You're not adding as much in terms of your connections. Manufacturability is very compatible with ideas of modularization, both in the motor and inverter. One specific group in University of Wisconsin-Madison, no, that's not this one. I have another reference later. A group in Wisconsin-Madison is specifically working on creating a modular concept for these IMDs. They want to make it to actually add and subtract more like a daisy chain and convert them into not stackable, but ones that you can increase. So in the integrated drive, if you look at the Tesla Model S versus Tesla, it's just a comparison of the traction inverters. The challenges that tends to be is that if you have high power electronics, reliability can be a challenge, which means you need to at least make sure these electronic units are going to outlive your bearings. So if you die out sooner, then that creates a reliability and a life cycle issue. You need to have improved inverter thermal behavior, because you need to make sure you can handle at least 200 degrees Celsius. It needs to be thermally rugged so that it can actually handle the repeated temperature swings. You don't always stay at a constant temperature. The engine gets hot, it gets cold, you operate in a cold environment. Unlike any other system like an HVAC or anything domestic, those are exposed to a very narrow band of temperature. This actually gives you a very wide swing in temperatures that the ambient the system has to handle. You need to also be looking at cost reduction in power electronics. So the next one is actually 800 volts. We had a question about this as well the other day about what happens. Can we do 800 volts? Is anybody doing it? I actually did go ahead and update some of my slides because some of the information was available over this last few weeks. And current challenge, of course, is that we are trying to design a system, let's say for 50 kilowatts. And let's assume it's going to, let me rephrase that. Let's say we have a 50 kilowatt system that needs to be charged. So that would actually take about 35 to 120 minutes to charge the battery pack. Now, if you go from 50 to 150 kilowatts, you can reduce your charging time by about 2/3. Now, if for the current level of voltage, which is at 400 volts, you will get 3 times the current rating. Okay, what does that mean? It gets bulky. Your conductors will have, keep in mind it's I square R. Your conductors will have 9 times the losses. And that means you need to have improved, actually this is improved, meaning it requires an improved cooling system. So you will have to redesign the cooling system for the given 400 volts. You cannot just run it at 400 volts the way it is and hope to get the power level that you're looking for, or the charging speed that you're looking for. So in terms of the industry adoption, if you look at who's doing what, there are a few examples. Actually, I think even in the PDF, you should be able to click on that. But the Porsche Taycan, for example, has an 800 volts DC bus. They currently have that available. They can charge up to 350 kilowatts, and it can go 50 minutes to charge an 87 kilowatt hour battery pack. ABB has what's called the Terra HP, which can charge both at 400 and 800 volt batteries with either the charging capacity of 175 or 350 kilowatts. Whenever you go through that kind of a range, you are now designing a system that needs to be able to handle both high current and high voltage system. That's where the challenge oftentimes comes to be. Prius did 650 volts. You might remember they did that once, but they were doing it only for the traction motor. After that, Delphi actually announced an 800 volt silicon carbide inverter. Hitachi combined forces with somebody, and they actually came up with an inverter power module as well. So they were joining forces specifically with some company. Kia has the EV6, which has an 800 volt system. It can charge from 10 to 80% in 18 minutes. Hyundai has an EV global modular platform that will give you 800 volts, and it's currently used in the Ioniq 5. So what I'm trying to say is that what is interesting is, while we are thinking that issues like fast charging or issues like refueling time is a problem, there are companies who are actively pursuing this. This is why I was saying, when you start thinking about whether you can go to 800 volts, you need to go from device up and see what are the challenges, what are the opportunities. If I increase my voltage, things fall apart. Can they be fixed? If I get that to happen, what is the value proposition? So your idea always is bridging. Your idea is going to bridge what the challenges combined with what the output needs to be. If you bridge that gap, you can very effectively define your PhD topic, or basically define your research topic, or better yet, you can start a company. So this is just an example once again for comparing the Porsche Taycan and the Model 3. The Model 3 basically has a 400 volt DC pack, and then you have Porsche that basically has an 800 volt pack. What you will notice is that in terms of the peak voltage, when you go for 96 cells versus 192 cells, obviously you're going to change the number of BMS units required, right? If you have 96 cells, you have a certain number of BMS units. You go to 192, you double the number of cells. Now your requirement on the complexity goes high. So there's benefits absolutely by going to 800 volts, but it's not a free lunch. There's always going to be something that's going to get in the way, which means the benefits are you get a better, faster charging. You get lower I square R losses because it's V as opposed to I that you're pushing up. Your current density of the motor, the power density of the motor goes up, wiring size goes down, and it is very good for heavy duty vehicles. So it can be used for electric buses, it can be used for trucks, mainly because it can handle much higher power. Because previously, if you went for higher power, your current had to keep going up. Now you have given it more flexibility by pushing the voltage up. Now your power can actually go, which means now your electrification can go from a sedan and a small passenger vehicle to larger delivery vehicles. That's the enabling capacity for this. The challenge, like I said, your components have to be redesigned. You designed everything currently that's in use with a certain thermal behavior, right? Your contactors, fuse, cables, they're all designed to handle exactly what you have. If you try to upgrade your voltage level, you also have to redesign several of these auxiliary components. Your cell monitoring, that's an extra load for your controller. You might need a boost converter, like you saw for the Prius. You might need a boost converter specifically to increase the voltage so you can do fast charging. That also, of course, would mean if you add one more stage, we talked about that, efficiency takes a drop, right? You add one more stage, 90 times 90, 81. So there's also going to be a bulkier insulation. Instead of 400 volts or 600 volts even, you have 800 volts, which means now your insulation size, your dielectric that you're going to use for insulation is going to be possibly bulkier. More higher mechanical stress because you're going to operate at higher speeds. We talked about bearings, same idea. You're going at higher speeds, which means mechanically your motor is going to be more taxed. And you're going to have partial discharge. You will have ionic discharge because you have higher voltages. The breakdown voltage can possibly be overcome if you have very high dB/dt. So once again, in terms of the comparison, what this does to your battery pack, right? So in terms of the pack itself, if you are at 400 volts, you end up going to a BMS that costs you about 602 volts. At 800 volts, you go up to about $818 dollars. The gauge size basis is 3 versus 1, and your contact fuse rating goes from 500 to 900 volts, and the electrical clearance also needs to go up correspondingly. Qualitatively, in terms of what this does to your vehicle is what is interesting. At 400 volts, you're getting a very good bang for your buck on your BMS. Energy density is high. Cabling is where you actually get a much better performance when it comes to 800 volt system. Fast charging, better. Reliability, not as good, like I said, because you are talking about changing insulators, contactors. Whenever you're talking about all of that, losses got better, but now your safety requirements have to be increased. Keep in mind, anytime you go to higher voltages, your safety requirements, reliability, partial discharge, all of those issues now become very, very real. So this actually shows you, this is for the inverter losses that you get for 3 combinations. You have a 800 volts inverter, 800 volts motor, 800 volts inverter, 400 volts motor, or a 400 volts inverter and 400 volts motor. This is actually one of the papers that was submitted, and they actually showed specifically how this operates. This is one of the TTE papers as well. So what you will see is that in each scenario, you are actually able to get an inverter output. We can control the losses by properly selecting what voltage and what your inverter and what the motor voltage is going to be. If you go for a high voltage, high motor and inverter, your overall losses are going to be low. Why? Well, I square R losses went down again with you, right? Copper losses. In terms of this combination, here are the conduction losses, MOSFET, conduction again for the, and then you have switching. So diode, MOSFET, total conduction and switching losses. What you notice is that when you're talking about the 800 volts and 400 volt combination, your numbers are always going to be high. In particular for the total loss, switching loss and conduction loss. If you look at percentages, switching loss is the biggest jump that you see if you are 800 and 400. If you stay at 800, you're getting the least amount of switching losses. The point I'm trying to make here is not that there's good or bad. What I'm saying is there's a design choice. At any point, if you are a company, like we said before, they did a 42 volts, it didn't exactly go. I'm not saying it's a risk that's not worth taking. I'm saying the exact opposite. I'm saying right now is the time to be taking risks. But at the level, at a research level, whether it's a PhD or a research in academia, it is a very good time to test out something like this to see what your system behavior is going to be. What are the possible consequences of going to 800 volts? 800 volts is an emerging area. There's a few people who are doing it, a few companies doing it, but there's a tremendous opportunity. So what's the roadmap for power electronics going to look? This is just, once again, I use a lot of language from Department of Energy to kind of lay out what this roadmap looks like. So the first thing is, if you're looking at devices, you need to get to a place where commercially available wide bandgap devices needs to be available for use. They're not there right now, but we need to have them. They need to be commercially available. The second thing is we need the ability to integrate designs, and we need to get optimal use. Like I said, you cannot just look at any one specific device in isolation. You have to look at it in context. What does add in the device? If your switch can handle the temperature, can your sensor? Can your solder joint, can that handle it? What about the feedback? Is the throughput going to be fast enough? Is your bandwidth going to be adequate? You have to look at it all in combination. So you need to look at multi-physics integration. You need to look at thermal, vibrational, and structural behavior. And that's even for power electronics as well. For high temperature isolation materials, you need to see what kind of devices are available, what kind of material options are being developed. This is a very good time to to join forces with somebody in material sciences or chemical engineering, because this is the time when what they have known for quite some time in terms of material properties. If you know somebody who works in exotic materials and such, it's a very good time to see what it is that would enable you, identify the bottlenecks, and start to take them out, because that's what you will use to solve them. And of course, for the power electronic barriers, you need R&D that basically addresses core technical gaps, which means you need to look at the domestic supply chain, you need to look at miniaturization and cost optimization. Everything that affects cost is going to affect technology. If it means you're going to import stuff, it affects the technology. If it means a device becomes less available, also affects technology. The point being, or even if you have expertise that goes out to a place where you are having to outsource a lot of your expertise, that adds to the cost, which is why a lot of companies start to bring them in-house so you can actually do the manufacturing and the development yourself. So strategy-wise, here's what they put out in terms of what these numbers should look like. So if you look at the potential pathway for getting to the $3.3 per kilowatt, you need to first deconstruct the traditional component boundaries. You cannot start thinking in isolation. You have to take that apart. This component integration, and then of course here you have multi-physics integration, additional component integration, and then device application. So basically what I've been talking about this last 5 days, it kind of summarizes at least the idea behind that. In terms of cost though, what you need to do is you need to have a power module that costs you less than $59. You need to have a bus capacity that's going to be less than $30. What that looks like, you have to look at your market. Because if you want to meet that target, this is how they came up with the numbers. They added all of them together, and then they said $270 is what it should cost. Right? So the same thing, if you look at electric motors, same idea applies. Potential pathway for getting a 4.7 or 5.7 kilowatt per liter or $4.7 per kilowatt, you need to have material developments. That's your first step, because that's something that we have not done as effectively. A lot of work is happening right now, but work has been happening in isolation. You need to look at electrical steel, what you do in terms of manufacturing processes, whether you're doing stamping. That's why we talked about specifically the idea of stamping and winding design and everything. You need to figure out how do you make sure that the impact of your lamination cutting does not deter you or does not affect your overall performance. Low cost, high efficiency, low cost, high efficiency steel, and of course our pet topic of removing rare earth materials. We need to find a way to get permanent magnets that are just as good, or you need to have motor designs that are just as good. So in a lot of cases, you might compensate for one with the other. That might be an acceptable trade-off, but it is something you will have to prove. In terms of the dollar targets, you need to have carbon nanotube-based copper materials. They basically can have design and long-term characteristics. We need to characterize them, and replacement of magnets with soft magnetic materials. So There are lots of opportunities for us in terms of cost of the motor itself. Your stator takes up about 39% of the overall motor cost. That needs to be brought down. Your rotor is next. That needs to be brought down to $70. That combines everything together to take you to the total amount of $330. Now, keep in mind, there are some cost caveats to it. When you're designing a motor like this, like we just having the conversation, you might be reducing the amount of active material used. Let's say you took out, because of flux manipulators, you took out more content. The question does come down to, does that save you money? Meaning, if they are basically using, they're removing material or this lamination material from the sheet, that's waste, right? So it's not zero waste system. So there are mechanisms that people have come up with which actually creates not zero waste, but it's a very low waste system in which you place the lamination and stack them specifically in a way that allows you to create almost zero waste. But the slots that you cut out, that will be wasted, which means you can modify it, you can adjust it, but where you're going to get cost benefits versus where you're going to get efficiency benefits might not always be the same thing. So with that, I wanted to kind of take it out to our closing remarks. Like I said, at this point right now, no matter which country you're from, whether you live in the US, whether you live in anywhere in India, Singapore, China, you name it, everybody right now is looking at options for HEVs and EVs. The market is very, very hot. There's a lot of work going on. The challenge is there is a lot of work going on. So as a researcher, one of the things that I definitely will say is there's lots of advancement that has been done, but there's a lot more that has to be done. I mean, even as I've only been in this area for a couple of decades now, but even in the last couple of decades, what I know is barely scratching the surface. There's a lot of details that I'm still learning in real time, and you find out every single day what you don't know. The more you acknowledge that, the more you accept that, the better it's going to be. Otherwise, you'll end up getting stuck in a place where you might not move forward as quickly. And of course, your cost and all-electric range are two very important aspects. What you are selling is very important. People care about how much they pay today. People care about what it looks like, but more importantly, people care about how much they're going to pay for running it, right? Cost and cost. Look is great, but right now most cars look great. So you can have something that looks like a Lamborghini, but the reason why the Lamborghini is so popular, arguably, is because it's a Lamborghini. Right? I mean, like you're not buying it. I mean, a lot of I don't have one, so I cannot even make that statement here. But if I was to buy it, I would buy it because it's somebody says you're driving a Ferrari. I'm not going to ask you how many, I don't know, how many seats does it have? Is the AC effective, or does it have a traction motor? No, it's a Ferrari, and that's all you need to know. Right? Beyond that, I'm not telling you anything more because you shouldn't have to. So the point I'm trying to make is that you have two of those categories. You have the Cadillac people who are right now, which by the way, like I said, the Cadillac, the new one, Lyric, is about $60,000, which is not as high as one would think. The Roadster, when it came out, was close to 100,000. Rivian and Faraday Future are coming up with Faraday Future is coming up with their cars that is at about 180,000 base. And then you have Karma that is coming up with their vehicle at about 120,000 base. In comparison, Cadillac from GM stepped back and said, we are going to be at 60,000. The point I'm trying to make is that the whole idea of cost is very, very relevant, but it's a trade-off. Like, what are you giving up? As I understand, Faraday Future will have a full experience where you will actually have a full, I think they said a 20-inch or 24-inch monitor or something in your back seat. So they're designing it, and once again, I'm not, this is based on my observation and the discussions I had, they are designing it not for the driver. They are designing it for everybody else in the car. Chrysler Pacifica, seats, there's screens on the back of every car, every seat. So the second row has their own screens, like an airplane. So the question has come down to me, like, in terms of innovation, where is that going to be? There are companies that are doing, Ford is doing that dash, the display on your dash. It's great. What's the cost? What's the trade-off? If there's a crack in the windshield, is that more or less expensive? Because if you're driving on the highway, getting gravel that hits and creates a crack is doable. It happens. What's the cost of replacement? What's the cost of maintenance? The point I'm trying to make is that cost has a lot of facets to it. It goes everything from what I'm paying today to what I will have to pay until I sell the car, or hopefully keep it for life. How much did I pay? And the last one, of course, is if you want to have optimal performance, you need to start looking at every single variable. So the overall theme that I have kind of based my research on over the last decade and a half has been in looking at multiphysics. And the more I recognize the need for it, the more I realize there's potential to combine them together. So on that note, I just want to kind of leave it out here for anybody if you have any questions. But I wanted to just thank you very much. I know you guys have spent a lot of time listening to me talk, and I've gone nonstop for quite some time. So I appreciate your patience. Thank you for your time. I look forward to the next session when I'll get to hear you guys for a change. And if you have any questions in the meanwhile, let me know. So when they're talking about it, oftentimes at high speeds, you're talking about having a uniform, the solid rotor essentially will reduce your windage, it will reduce the centrifugal forces and such. So yes, there will be a trade-off. You are correct. Solid rotor core is not always a solution to the entire problem. It is one of the variables that you do have to consider for your trade-off. So it's not, I agree. I think the language might have made it sound like it's a fix. It's not a fix. It's just one variable that you can control or you can manipulate. Any other questions? And we can talk more. I mean, like I'd be more than happy to, when we meet at 2 p.m., I'm more than happy to talk about other things. Some of the questions have already been sent to me yesterday. I'm more than happy to, I mean, those I will definitely talk about. But if you have anything that we do not include, let me know. So if that's it, guys, thank you very much. I appreciate your time. You can go ahead and have lunch, hopefully. And then when you come back, we will have a session here, right here. Don't go any other place. You're going to come right back here for the demo. And then we'll do the Q&A session and then close up the day. Right? Thank you very much, everybody.